Cool. So what is Python? Also appreciate the little memes that we've embedded everywhere. So Python is obviously a very, it's one of the most loved programming languages. It's very useful, and it combines like different elements of C++, Java, as you can see here. It's a procedural language like C. It includes object-oriented programming like C++. And there's so many different things that you can do in Python, like scientific programming, object-oriented programming, data visualization, and much, much more. So just to kind of highlight some differences between Python and C++, one very obvious one is there's no semicolons. The syntax is much cleaner and nicer, and it also just makes more sense and intuitive. Like there's things like input, output, print. You don't have to do all kinds of like cout and cin statements and handle stuff like that. And oftentimes you don't need to initialize variables ahead of time. Python is pretty smart and can decipher that on its own. And then we're going to go through several different functionalities of Python, just quickly, because I know most of you are already familiar with this. Yeah, so there's different data types like any other programming languages. There's integers, there's floats, there's strings. One of the key differences or unique components of Python is that there's dictionaries. And this is kind of how you declare a dictionary here. And then there's also tuples and lists. So instead of arrays in C++, Python has lists and tuples. So tuples, once you declare a tuple, you can't change or assign its value afterwards, it's immutable. But with lists, lists are basically like the array version of C++. And of course, we have strings in Python. User input is a lot easier in Python because we just call the input function instead of doing some hooky stuff in Java and C++. Yeah, so that's just some examples. This is an example of a list. And what's nice about lists is you can append to them. Unlike C++, where when you declare an array, you can't change the size of it later. In Python, lists, you can change the size of them, append values to them in a for loop. You can remove stuff. There's already built-in functions to count the elements in the array, sort them, find the max, all kinds of things. These are just a couple of examples. Yeah, and then just a refresher on how you would do the syntax for conditionals. It's very similar to other programming languages. And of course, there's loops, both while loops and for loops. The syntax is different. There's this range component for for loops in Python. You can either specify a range or not specify a range. It really depends on the kind of program that you're writing. And functions. So functions, this is just an example of how you would call a function in Python, just like any other function, and how you would define it. There's also a nice thing about functions in Python is you can put default arguments. And when you put a default argument, that means that when you call the function and you don't input, say I have a function called birthday, and it only takes in one argument, name. But what if I call the function, I want it to have some default value if I don't pass in a name. So the default name is, say, Adwaita. So you can do a default argument in Python by doing equal equals Adwaita, and that becomes a default argument. So every time I call that function without anything passed through, it will automatically use Adwaita as the name. And so this is a little summary. You guys will have access to these slides during the tutorial and also afterwards. So if there's anything you forget about Python and want a little cheat sheet, this is a short summary. And I'll let you guys just look at that for a couple of seconds. Okay. So now we're getting to the exciting part. This is going to be a little intro to decision trees that will lead up to the tutorial that you guys are going to be doing with us later on. So what is a decision tree exactly? And it kind of resembles the shape of a tree, as you might imagine, except when we're talking about decision trees in programming, the tree is actually inverted. So instead of going from the roots up to the tree, you start with a root at the top, and then you branch out into different leaves and nodes, and we'll see that a little bit later. Okay, so this is an example of a decision tree. And so as you can see here, the ones that are highlighted, these are kind of your, hold on, I need to, okay. So yeah, this is an example of a decision tree. The ones that are bolded in black are called the nodes. And then from the nodes, you kind of branch out and you can see the branches that are signaled by these lines here. And then we have something called a leaf node. So a leaf node is when you're kind of done with the decision tree. It's like the ending decision that you have ended up at, and the leaf and node doesn't split further. Okay. Oh, and I forgot to mention, so what are some benefits of even having a decision tree? Like why, maybe some people can participate, sorry, what is happening? Some people can participate. Why do you think it is meaningful to have a decision tree in the first place? Anyone jump in?
To make decisions.
Yes, yes, to make decisions. Can you guys still see my screen? Just the Zoom settings was, okay. Yeah, to make decisions. And in this particular case, so everyone's familiar with the Titanic, I'm sure. And so there was obviously survivors. We can classify there to be survivors or not survivors in the Titanic. So we can use a decision tree to basically predict whether a passenger survived or not. If I give you a whole bunch of data that has, say, the gender, the age, you know, the color they were wearing, I don't know, some random information, and I tell you, did this person survive or not? It's going to take you some time to comb through the data and figure out, like, oh, like, let me look, did this person die? What was their age? Did that affect if they died or not? So a decision tree is like a way to visualize data and for your machine to more easily sort through the data so that when you ask it a question, did passenger A die in the Titanic, it can more easily give you the answer. And so I kind of mentioned here where the tree splits, we get branches and edges. And when the branch doesn't split anymore, we call that a leaf. So this one would be an example of a leaf. That's like your final decision and what the tree returns. And now I'm going to start presenting, and Adwaita will take over for how to determine when a split occurs.
All right, cool. Thanks, Radhika. So here we're looking at just like a basic node with two leaf nodes coming off of it, just like a split in a given decision tree. And we're going to talk about how a machine finds the best split, or your machine learning model, because obviously it goes through tons and tons of data, and it can ask the data essentially a series of questions. Each node is a question. It like asks the data, and then using that, it sorts the data into like different groups. And the idea is that you want to get each group it sorts data into to be as homogeneous as possible. So here we see that C, which like this C0, C1, C is the target variable. It's what you're trying to find out about the data. So in the Titanic example, it's whether or not the passengers survive. So what you want to do is you want to make sure that each group that the data is essentially split into as it keeps going down this decision tree, each group becomes more and more homogeneous. So either the group has all people who survived or all people who didn't. So I'm going to look again for a little bit of participation here. We have two examples, A and B, of two different splitting variables. Oops, let me go back. And I want to know which one is the better splitting variable, kind of based on what I just said. Once I get back, we will see. Uh-oh. Do you want to like exit out and then like share again or something. Yeah.
I'm really like bad with this. Apologies.
Oh, good. Technical difficulties are given. All right, so can anyone tell me which splitting variable seems better? And feel free to unmute yourself or put it in the chat, A or B.
A.
Unfortunately, that is incorrect, Max and Yvonne.
We
the
tried,
answer would be
Yvonne.
B. Yes, unfortunately not. It's because B has results in groups that are homogeneous. You see node 3 and 3, C0, there's 9 of C0 and only 1 of C1. But on the other example, I can just keep going, there's 1 of, I think, C0 and 9 of C1. So essentially you have two groups that are mostly either C0 or C1. You thought they were the values. I probably should have done a better job of explaining the graphic before asking you guys the question. That's okay. Good effort. I appreciate that you guys volunteered. That's a big deal. But yeah, so we can keep going. So there are ways that your machine or your machine learning model obviously measures this, because no one sits there by hand and calculates like which question of all the different attributes you're looking at actually result in a better split that leads to more pure nodes. So one of these measures of impurity is the Gini index. So essentially this is just like a mathematical formula you can use to find out whether or not your node split is pure or not. So I'll explain how this one works. Again, like I said, you guys will never be doing the Gini index. I wish it seems like they misnamed it. Gini, useless. Gini, that would have been better. No, but so here, if you look at this, the way they calculated it, you can kind of see it down here where it says Gini equals 1 minus 1 6 squared and all that. Essentially what they're doing is they're calculating how much of the total belongs to each group. And then they plug that into P J given T and they square it. It's an equation. Again, you'll never have to use it, but the essential idea is that the closest you get to 0.5, it means that the data was evenly split between the different groups. So if you get a Gini index of 0.5, that's really bad. Your node did a horrible job. But if you get a Gini index of 0, that means that your node is really pure. And essentially the two groups that your node created have all of, are very homogeneous. They have all of whichever group they are supposed to have. So they're very pure. So that's what your computer is trying to do when it goes through and creates the tree, except it does that like obviously like a bajillion times, which is why it's machine learning and not like something we can do. All right, so if we go to the next slide, we will see another measure, which is entropy. This is kind of the same idea, a little more complicated equation, but it's the same thing where if you have a minimum of 0, again, you want to get 0 because that means that your node is the most pure. So we keep going. So when you work with machine learning in general, you guys might have heard that you can have a model that becomes either underfitted or overfitted to the data. So the idea of overfitting is that when you train your machine learning model, you give it like training data so that it can learn from that and then create the model. But when your model becomes too well fit to the training data, it becomes too good at the training data, it becomes really bad at everything else because you can't extrapolate the same model into other new test data. So that's what happens when we have overfitting here, which is this red dotted line. You can see that the error percentage is really low for the training data, obviously, because it's trained on the training data. And so it knows it really well and it can predict that successfully. But then you see the percentage error actually going up for the testing data, as in the new data you're introducing to see if your model is any good. And that's because your model is overfitted to the training data. On the other end, you can see like back when I think the very beginning of this top left of this graph, your model can also be underfitted, as in it hasn't seen enough data and therefore it doesn't really know enough to make any useful rules. So you have to watch out for this when you're making your machine learning model. So we keep going. For decision trees specifically, the best way to address overfitting is to grow your tree out to the maximum. Essentially, you grow it out so that every leaf node is completely pure or as close to completely pure as possible. And then you like trace back. You cut off branches or you tell your model to kind of stop branches at certain levels so that once you know how it is completely overfitted, you can kind of scale it back till you get to a level where you've balanced the accuracy of your model so it's accurate even for testing data. That's not something we'll be doing today in our demonstration because that would just take us a while to all code together. But in practice, if you're using a decision tree for something else, that's something you would want to do to make sure that your model works.
Adwaita, I think we have a question.
Ooh, we have a question. I cannot see that.
Yeah. Oh, I had a question. So can I just like reiterate some of the things that you said just to make sure that I get it? So each node in a decision tree represents like a literal decision. So you can take the data set and prune whatever condition you want out of it, and you want it to be as equally balanced as possible. But why, like intuitively, why do we want a more split tree? Because like we're gonna run through it like all the iterations possible and then pick like the most evenly split one using like the Gini index and the entropy index, right? Why is the evenly split tree better than one that's like maybe imbalanced? Theoretically, conceptually.
Clarify what you mean by like evenly split.
Because you said that you want the splits to be homogeneous. Why does it have to be homogeneous?
Okay. Yeah. So by homogeneous, I just mean that like when you split it, you get like two groups, like one where like all the data points towards like one classification and the other one's like the other classification. So essentially because you're classifying the data, right? I might not have explained that properly. So you want everything to be properly classified so that when you go through, let's say you have an example piece of data and you trace down through the decision tree, you come to the correct classification. That's the goal of a decision tree. So the reason you would want to make sure, reason you'd want to prune it back is because since you're going through this decision tree and you're coming to a certain conclusion, that's the classification of that piece of data, you don't want it to be over like that specific classification to just work for the training data you have, which is why you're going to prune it back. Because that's how you would avoid overfitting. Because or else your decision tree will just keep going, your model will just keep going until it gets like perfect classifications, but it's only perfect for your training data and you can't use it anywhere else. Does that make sense? Okay, cool. All right, so we can keep going. All right, and this is specifically today, we're going to be using sklearn, which is a library in Python that just has like a lot of cool machine learning functions and stuff. And that's where we'll be using our the functions we're using to create our decision tree. This specifically, that function doesn't allow you to take in categorical variables if they're just like, ooh, wait, I have another question. When is entropy used and when is Gini? That's a good question. It's entirely up to you. Honestly, today we'll be using Gini just because that's like the default setting on the function we're using. But you can, I guess, go through and decide if you want to use one or the other. It's more like that these are two possibilities you can use. As far as I'm aware, there's no advantage of using one over the other. I think entropy might be, also, yeah, actually, I don't know. I don't know why there would be a specific reason to use one or the other. One might be more, I think entropy might be computationally more expensive, but also marginally more accurate. That could be the difference.
Well, thank you.
Mm-hmm. All right, cool. So, oops, a little far. Essentially, what we're going to have to do is we're going to have to take our categorical variable. So a categorical variable is essentially like male versus female, or here they have like 4 different types of pets. These are not numerical, essentially. So if you have 4 pets, you might have like bird, cat, dog. Like those obviously aren't numbers. And you're essentially turning them into numerical variables that the model can accept. So that's what a dummy variable is. So here we can see they took this, this categorical variable, pet, and they turned it into essentially 4 different attributes that have a 1 when it is that type of pet, and then a 0 because it's not the other ones. So this is just something I wanted you guys to see because we'll be doing it in the coding very shortly. But yeah, essentially this is what we'll have to do. You'll have to do for variables such as like gender and other things like that, at least for the function we'll be using. All right, cool. And so now we are going to be doing a demo where like you guys will hopefully be coding with me. We're going to be taking the Titanic data set. I've been saying a lot about Titanic data set because we'll be using it, and we'll be creating a decision tree model that will help you predict if any given passenger like survived or not based on, you know, the given passengers we have. So this is just an overview of the data we have from like the data set that you guys hopefully received in an email from Jenny, or I can pull from GitHub. Essentially, it has what class the passengers they were in, their gender, the age, who they were related to, that was also on the ship with them, their ticket, and some other like, you know, information. You guys can come back and refer to this if you want to like know more, but we'll be using it to determine which attributes we want in our model, or we want to add to our model to train it, and which ones we want. So I think we can stop sharing the slides, and I will go ahead and share. Oh yes, and these are our sources. A lot of classes, clearly. Help us out with this. All right, cool.
Okay, I'm gonna stop sharing. I'm also going to link the slides in the chat in case you want to refer to them.
Okay, cool. Can you guys see my slides? Or not my slides, just like my screen. Yes, awesome. Okay, so we're going to be coding today on Jupyter Lab, which maybe some of you guys have used, but essentially it's just like an online place we can code Python. So if you guys could just like Google Jupyter Lab and pull it up on your computer. If you go to jupyter.org, I can even put this link in the chat. It should look like this. And if you just click try Jupyter Lab, it should load up for you. It takes a couple minutes or a couple seconds, but it should come up. And essentially this will let us like upload the data we're going to use and then pull from it to code with it on Python. Okay, cool. So hopefully you guys can still see my screen, my Jupyter Lab just pulled up. What we're gonna do is we're gonna first open a new notebook. So the way you do that, there's a little plus sign in the top left corner. You can just click that and then click Python. This opens up just kind of like a new file for us to code on. You can also do like cool things like markdown cells if you guys haven't worked with Jupyter Lab, but we'll just be using it for coding. Also, first, before we start coding, I'm going to have us upload the data file to Jupyter Lab. Do you guys have access to it? I can also drop it in the chat if you guys don't have it. It's the Titanic training data set. Do we have it?
I should have sent it out in the email. So if everyone
TitanicTrain.csv.
Yeah.
I
If you
can
look
put it
back
in
at
the chat. It's
email
on the GitHub.
too. And on the GitHub.
It's there, right?
Yeah, if you pull the entire repo, it has everything.
I'm just gonna upload it. All right, cool. So it should show up once you guys put it in on the left-hand side of titanictrain.csv. So hopefully all of you guys have that. So first, before we start, we're gonna upload all of the libraries we're gonna use in this exercise. I'm going to drop them in the chat because there are a lot of libraries. And oh, thank you, Jenny, for dropping the CSV file for those who are GitHub challenged like I am. Here are all the libraries we're going to use. That looks like a lot, but we actually will be using all of them. I'm going to quickly explain them while you guys kind of copy paste it into your cell. And then in order to run a cell, by the way, you have to just click this little play button at the top and there'll be a little star on the left, but once that turns into a number, here it says 1, it's run. That's how Jupyter Lab works. All right, so these libraries, NumPy essentially allows you to work with arrays on Python and like do like matrix algebra and things. So we'll be using that. Pandas allows you to use data frames. It's really good for big data sets. Essentially anything you do with machine learning on Python, you'll probably use Pandas because that's how you'll be like looking at some element of your data. Then we have matplotlib. So essentially matplotlib is the way for you to use like MATLAB functionalities on Python. I don't know if you guys know what MATLAB is, but essentially it stands for Matrix Laboratory, and it lets you do like matrix multiplication and like array stuff along with like cool like plotting and data visualization stuff. It's like its own coding language and stuff, but it stands for an annoying language. Yeah, if you're a BME, like I think very few of us on this call are, you have to learn MATLAB very well. Arrays start at 1. Okay, wow, a lot of opinions on MATLAB in the chat. Okay, moving on. And then we have Seaborn, which is another data visualization Python package. We'll be doing some graphing with that. And then finally, we have sklearn, which is the machine learning library I was talking about. That's where we'll be pulling our decision tree functions from. Okay, cool. Hopefully everyone by now has the libraries loaded in and, you know, has everything up and working. First, what we're going to do is we're going to read in our CSV file. So I'm just going to name my data frame df, and I'm going to read it in using pandas since it is a CSV file. And then of the file, and I run it. So technically our data is all loaded up. Obviously we want to see our data, so I'm going to have us print it. I'm using .head here. Head is just a function that lets you see the first 5 lines of code. So as we can see, my data loaded, and we can look at the data here. There's passenger ID, whether or not they survived. 0 means that they died. 1 means that they survived. Their class, their names, sex, age, and all the information that was as promised. Obviously, it can be hard for us to look at big sets of data by just looking at them, like with the .head. It doesn't really give us much information. So I'm going to use a function called describe. This essentially gives us like basic statistical information on any numerical values. In any of the quantitative information here, we can get data on it. So we can see like mean, standard deviation, like percentiles and stuff like that. This can be helpful with for if we just want to like understand the data we're looking at. A lot of like data analysis is honestly just like exploratory data analysis where you look at numbers and you go like, that's cool. So this kind of helps us start doing that. Since obviously we want to build a model where we're trying to like find out some correlation between, the attributes and our target variable, where I'm going to use a function called core, which just stands for correlation. And this will tell us, will essentially calculate the correlation between all of the given variables. So if we see like, if we want to look at the correlation between survived and passenger ID, we see that there's honestly no correlation. The way correlation works, I don't know if you guys have taken like a statistics class or seen it in class. Essentially, the closer you are to 1 or -1, the stronger correlation you have. So a correlation of 1 means you have like just like a straight linear relationship. Often you don't have that, but 1 specifically is like a positive linear relationship. But if you get close to that, that means that 2 variables are more strongly correlated. So for example, we can see here that something that seems, okay, for example, passenger class and fare are pretty highly correlated, obviously, because what class you are determines how much you're paying for your ticket. So things like that we can look at. Specifically, if we're looking at like survived, we see that passenger class seem to like determine survival. 0.33 is honestly higher than a lot of these other numbers that we have. So these are things we can start looking at to see if we have correlations between variables. Okay, so correlation is not really easy, as in like looking at these numbers doesn't tell us an awful lot. So another thing we can look at, we can use is Seaborn has a function called pair plot that essentially will let us look at all of these variables plotted against each other. So I'm gonna put that in here. I'm also gonna do it based on survived. So we're gonna see these, when the graph pops up, it'll make a little more sense. But essentially we're gonna see all the variables plotted against each other and then color coded based on whether the passenger survived or not. And I'm also setting our bandwidth equal to just like a random number. JupyterLab unfortunately requires that. But if you guys run this, this should, invalid syntax. If you run this, you should get, after a little while, this takes a while, like the graph that plots everything against each other. Along the diagonal, we'll see histograms where we just see like the distribution of any given variable, but everything else should be our variables plotted against each other. So whenever you're plotting something, you have to do plt.show, or I guess you don't. But can you guys see this? It's kind of small, but essentially these are all the variables plotted against each other. When you guys are doing like data analysis initially, this can be really helpful to see what variables really matter and what determine, in this case, survival, since I did it based on survived. Are these plots sort of pulling up for you guys too? I'm gonna pause here and see if anyone has any questions or if something isn't working for anyone.
Oh.
Whoa. A couple people talked.
My pandas can't even see the CSV right now. I don't know why. It's in the same folder and everything. Yeah, I've used this before. I don't know why it's not doing it.
Right name of the CSV.
Yeah, I renamed them both 1.csv and it didn't work.
I could try going out of a breakout room with you.
Yeah.
And
Yeah, that
then
might be better.
we can keep answering and going on the lecture.
Could you scroll up? I think I'm missing a line for like where DF is defined. Oh yeah. Thank you.
For the pair plot, what was hue and diagonal KWS.
Okay. So hue is just what's coloring our data. So we're coloring our graphs based on whether people survived or not. So I think blue is that they didn't survive, so 0. And then orange is that they did survive. So usually you would set this to your target variable so that you could kind of see everything in terms of your target variable. And then the diag QWS, for some reason JupyterLab requires you to do this. If you were to like run this command or run this line of code, honestly, on literally anything else, I was using PyCharm, for example, you don't need this, but essentially just sets the bins, the bandwidth of these horizontal histograms to 2. And for some reason, you need to assign a value to that for JupyterLab.
All right, thank you.
Mm-hmm. Okay, cool. Any more questions? If anyone has any questions, please interrupt me. I don't want to just like keep talking. You guys have no idea what's going on. Okay, cool. So we kind of are looking at our data, and that's kind of cool. I guess we can see some interesting things, such as, for example, everyone who died had a really low fare, or a lot of people who died. That seems to make sense. Ooh. Okay, so thank you, Radhika, for throwing the code into the chat. That's probably helpful. But yeah, so there's some cool things you can see, but we're going to keep going so that we can finish this tutorial on time, hopefully. And what we're going to do is we're going to start cleaning our data. So we started looking at it, but we want to make sure that it's clean data so that when we do eventually put it into our model, or when we do more exploratory data analysis, and we want to just like look at it some more, we have nice data for us to do it with. So what I'm going to do is I've kind of gone through the different attributes, and I've decided preemptively before this tutorial that there are some things that are essentially irrelevant to our code. So for example, the cabin number was randomly assigned and has nothing to do with whether or not people died, because their cabin numbers are random. Same thing with their passenger ID, and their name is cool, but again, doesn't really matter for us in terms of whether or not they died. So I'm actually gonna put this line in the chat, it's a little long. But I'm going to drop a bunch of columns. So df.drop allows you to drop any columns or rows, actually, if you decide to drop certain rows from your data frame. And if we run that and then we see our data afterwards by doing .head, we can see that certain columns have been dropped. So we already have a much smaller data set than we did before because we took out just irrelevant variables. Now we also want to see if there's any null variables in our data. So, because obviously we have you can't throw null data with null values in our variables, null values into our model. So we're going to go through and see where those are, because they're definitely missing. So what I'm doing is df clean, which is the name of my new cleaned data set. I wanted to save my original data frame so that just in case I want to go back to it, I still have it. And so df clean dot is null, which will check if anything is null, dot is any. So this will go through my different columns, my different attributes, and tell me if there's anything null. So most of these don't have any null values, which is good, but we see that age and embarked, which are both true for having null values, which means that they have null values and we need to get rid of them. So I've looked at the data and I know that embarked is just I think where the passengers got on or where they boarded. So I also don't really think that's a particularly useful column for us to have. Ideally, if you were doing this, you would go through and you would graph the data and understand if embarked really had any effect on whether or not, a passenger survived. But for now, I'm just going to tell you that it doesn't, and we're going to drop the column because it has no values. Also, there's just no way for us to replace where they boarded with reasonable replacements, such as a mean or a median or something like that. So that dropped, which is great. And now what we're going to do is we're going to look at the distribution of age, because we want to. Yes. Do we have questions? Oh yes. I can definitely slow down. I also want to get us wrapped up. So hopefully we may not be able to finish all this, but guys, if you need me to slow down, please let me know, because I realize I'm going a little fast. Also, I'm going to start dropping a lot of the code just in the chat so that you guys can just copy paste it. All right, cool. So what we're going to do is we're going to look at the distribution of age. So when you're replacing null values in a data set, and it's like, they're like numbers, so we can replace numerical values. You want to either replace it with the mean or the median, because you don't want to like change the skew of your data or put in like random values when you're replacing null values. So in order to understand whether we're going to replace null values with either the mean or the median, what we're going to do is we're going to look at the distribution of the graph. Oh, sorry, this too. The distribution of the variable. So essentially what this is doing, what I put in the chat, is it's using matplotlib. So this is the exact, if you guys have used MATLAB, this is the exact same syntax you would use for coding it in MATLAB. But essentially what this does is this creates a figure 2, because we already have a figure up here, which is this. Figure 2, it's using just the age column. So we're just going to look at plotting that. And it's doing it as a histogram. And essentially then we give it a title, an X label, a Y label, and then we want it to show. So this shows us the distribution of the ages of the passengers who are on the Titanic. So as we can see, there are a lot of young people. And in general, this has like a positive skew. Since the data is not normal and it has a positive skew, what we're going to want to do is when we're replacing null values inside of the data set, we're going to want to replace them with the median. Does that make sense? And not the mean value. So I'm about to replace this here. You know what? I'll replace it with the median right now. Okay, I'm going to drop this line of code in the chat because this is long. But essentially what this does, it uses .lock, which is just a function to slice any data from the data frame. And it's taking what the data that is null, dfh.isNull, in the column age, which are the arguments for the .lock function, and replacing it with the median, which is dfclean age.median. And what this will do is it'll take all of our null values and clean them all up in the age column. So if you guys look at this now, if you look at the null values, you'll see that there shouldn't be any null values because we took them all out, which is the first big step in making sure, yep, so everything is false. So our data is technically right now cleaned up and we could throw it into our model. Does this make sense to everyone? Going a little fast.
What was the .lock again? Sorry, I missed that.
Yeah,
part.
no, for sure. .lock essentially just allows you to take like a slice of your data. So what we're doing here is we're picking out the pieces of data that have a null value for age. Yeah, I think it stands for locate, something like that. And we're replacing it with the median value. So we're replacing all the nulls with the median value, and lock allows us to locate that.
Can you, while Jenny and I were in a breakout room, you created df clean. Can you go back to that? Sorry.
Yes, of course. So df clean, I dropped a bunch of columns that were irrelevant, and I just set that equal to df clean. Yes,
Okay.
that was the access. Was there another question? I thought I heard someone else speak. Okay, I'm going to take that as a no. All right, cool. Okay, it seems like we're running a bit short on time. I had a couple other things planned for us before we moved on to the machine learning part, but I think I'm just going to have us move on. I will be sending out this file, or I'll send it to Jenny. I'll send out like the original Python file I had that has like a bunch more, or a couple more like cool graphing things and stuff you can do with either Seaborn or Matplotlib, just like other fun data visualization stuff that I don't think we'll have time to get to today. But essentially, before you like jump into like machine learning and throwing all your data into a model, it's a really good idea for you to look through your data and kind of understand it. And the best way to understand it is to make graphs so you kind of know what to put into your model. But I'm going to assume we did that. And I'm going to jump straight into finishing up cleaning our data so that we can move on to the decision tree part, which is the interesting part. All right, cool. So first, before we do that, we have one more variable, sex, that is a categorical variable, which means that we need to go ahead and get dummy variables for it. So the function for this is just get dummies. And what we're going to do is we're going to tell the function the column we want to get. We want to get a dummy variable for, if that's correct. And now if you look at the column, we'll see the same dummy variable that we kind of saw in the example slides I had. Also, again, because I wanted to keep our cleaned up data without the dummy variables, I created a new data frame. You guys can create new data frames as you want or don't want. It's just that if you ever need to go back to the data and like edit stuff, you technically still have it. So as you can see, it's split up sex into sex female and sex male. So because these technically say the same thing, when this data was created, they assumed a gender like binary. So if you drop sex male, just based on the zeros and ones for sex female, you'll be able to tell who's a girl and who's a guy. And because of that, I am going to I'm going to first assign our target variable and drop these extra columns that we have. So essentially what you're going to do is to put the data into the model, you're going to have to split it into our target variable, which is survived. We already know that. That's up here in our data set, and then into everything else, because that's just how the function is going to take it. So I'm going to set y, which is just my variable for the target variable, as just survive. Then I'm going to drop it from the rest of my data. So I'm going to create another data frame that has everything else. So I'm going to drop survive because obviously I just took it. I'm going to drop sex male just because it's repetitive. Does that make sense why it's repetitive? I'm going to set axis equal to 1 because it's a column. We're dropping columns. Okay, cool. So at this point, here, I'll put this in the chat. We have our target variables and we have our attributes separated into their own data frames. So now all that's left is to split this into our training data and our test data, and then to put it into our model. Does that make sense? Okay, I'm going to assume you have no questions here before I move on. Okay, cool. So what we're doing here in this line of code is we're just going to split the data into training data and test data so that we can put that into our model. As we discussed before, you're going to have a training data set and a test data set, so you can train your model on one and then make sure it actually works and it's not like overfitted or something in the other. So I'm going to very quickly explain. Train test split is a function that'll split the data for us. And it's better than splitting it by hand because this has a function or argument called stratify. It'll actually make sure that when it splits, it doesn't accidentally result in like your training data having everyone who didn't survive and your test data having everyone who survived. It keeps it even. What we're going to do, traditionally, you divide it up your data so that it's about 30% for testing and then 70% for training. So that's what this test size 0.3 is. And then random state, I've just set it to a random number. Essentially, this is so that when all of us run our data, instead of getting like different randomly generated like splits for each of us, we all have the same randomly generated split. Okay, cool. So now I'm going to go on and I am going to create the decision tree. Now this is just going to be kind of like a series of functions that we're just going to have to put in. What I'm doing, this is going to be creating the model with a Gini index, which we discussed before, and max depth equals 5. Instead of going through and like growing out the tree and then pruning it back and checking where I should prune it back based on like, you know, the accuracy of the model, I'm just setting the depth of our tree to 5. So there'll be 5 branches. This will also make sure that when we like come up with the final tree, we can actually see the whole thing on the screen, so else it gets really big. Okay, cool. Now I'm going to fit the data to our data set. So I'm using dt.fit. All this does is it takes our training data set, our X, and our Y, our target variable, and fits the model, which I named DT for decision tree, to it. So as we can see, it ran and we technically at this point have our machine learning model created. This is not too difficult. This part isn't too difficult. So now we are going to go on and we are going to predict how so we have like, you know, we have our testing data, which has, you know, the actual attributes and then the target variable based on that testing data, right? Because we have our entire data set, whatever that 30% of the original data. What we're going to do is we're going to use our model to predict a bunch of values for the target variable, and then we're going to compare it to our testing data. So we're going to compare what our model predicts to what the actual values are. So in order to get the predicted values, we're going to use a function called predict, as you can imagine. And all this is going to do is it's going to just take our testing data and put it into the model and pull out what our model predicts. So yeah, technically, this is like all we would have to do for the machine learning model. After this, we're just going to look at the model, but we've created all our data. So that was not difficult. I'm going to pause here again. Does anyone have any other questions about the machine learning part, any of these functions right here? Okay, I'm going to take that as a no.
I actually had one question.
Yes, yes.
So is this used like to organize the data before putting in an actual model, or is the decision tree just to like, because you said it's to like homogenize the data, right? The decision tree.
Mm-hmm.
So what is that used for? Like, when is that?
Yeah, so a decision tree can be used anytime you're trying to like classify data into certain bins, essentially. So the idea of homogenizing the data is just the idea that we want to put it into bins that give us some useful information about it. So right now we're trying to put it into bins that tell us that the Titanic passenger survived. So there's like a survived bin and then like a didn't survive bin. And that's all we're trying to do. And that's all the decision tree can do, honestly, just classify your data for you. It can't do much more than that, unlike, you know, maybe other more complicated forms of machine learning. So that's what you would use it for in general.
Okay, thank you.
Does that make sense?
Yeah.
All right, cool. All right, so now we're going to move on and we're going to check the accuracy of our model. We've created our model, we put the data in. Now we just want to see how accurate it is. So if I run this line of code, you guys should get the exact same answer as me because we removed elements of randomization early on. We get 0.82. So this means that 82% of the time, our model predicted accurately whether or not the person was going to die. The Titanic passenger was going to die, which is pretty cool. That means it more or less works. We can also create a confusion matrix for this. Confusion matrix is essentially a matrix that tells you like true positive versus true negative. If I run it, essentially just tells you how many of the cases were, you know, said correctly, as in people actually survived and my model said it survived. That's true positive. True negative, people died and my model said they died. And then on up here we have false negative, which is that they should have died, but my model said they didn't, I think, and then false positive. So this gives you a better idea of where your model failed. If it's doing like too much true positive or too much true negative, that'll give you an idea of like, you know, it's saying everyone survived and they didn't versus like vice versa. So it gives you more information on how accurate your model is. So now finally, we're going to just look at our actual model, look at the decision tree. I think this is the cool part. You guys can agree or disagree with me after you put that into your code. But essentially, this is exactly what our computer created. Can you guys see that on my screen? It's kind of small, I know. It's probably small on your screen too. But this is it. Essentially, it tells us if you were to the colors, I'm going to go through and explain this code. So the first, I just created a figure. I used subplot, but essentially I was just trying to create a figure of 14 by 7, which is like a big enough size for you guys to be able to see all of this. And then I created a tree called Titanic tree where I plotted my tree. I used, you know, the decision tree model I created. And what I did is I made it so that it was colored based on whether these people survived. So if it's orange, it means that they died. And if it's blue, it means that if they got down here, they probably survived. So this gives us an idea of just looking at our model, you know, what questions can lead us to like what classifications, if that makes any sense. And there's also a bunch of information. Each one just tells you like Gini index, it gives you some information. It tells you what attribute, what the splitting variable is. So for example, the biggest splitting variable was whether or not they were male or female. If you guys go back and look at this code at some point, I did some other graphs that I had, you know, that was going to have us do that we didn't have time for, that essentially would have told us that actually gender makes a big, big difference on whether or not the passenger survived or not, more than passenger class or how much they paid for their ticket or anything. And you can actually tell this by looking up feature importances. So this is another function that essentially will just tell us whether or not which features were considered most important to our model. So which really determined whether or not a passenger survived. So this is a little confusing because it's just a series of numbers that come out. But essentially, the higher the number, the more important that feature was in determining the final classification, whether or not your passenger dies. So you can actually see that 0.5, which is the highest number out of the 6 values we have here, corresponds to sex female. So again, this idea that your gender was the deciding factor. We can also see 0.18 is the next biggest one, has to go with passenger class. So whether they were first, second, or third class was like another big deal in determining whether or not they survived. All right, cool. So I'm gonna again pause here briefly. Does anyone have any questions?
Yeah, so I guess conceptually then, if you're trying to test it with some, what's it called? Like with a testing input that you have that wasn't used in the training set, then what it would do is that you would use a decision tree to evaluate based on the factors. Like if it was me, for instance, I would be able to go down the decision tree and be like, okay, well, I am a woman, like I am this age, I'm this class in theory. And then that's how it would predict for me whether I would have survived or not.
Yes. Yeah, actually, we can do that right now. It's the final activity I have for us planned before we finish this demo. Essentially, we are going to put a passenger in, and we're going to see if they survived. But just for kicks and giggles, let's put Jenny in and see if she survived. So what you're going to have to do is you're going to have to put in just a bunch of numerical data that corresponds with the columns. And we're using, essentially, put this data into an array. You reshape the array because predict, like dt.predict, only takes, the predict function only takes like multi-dimensional arrays or something, so you have to do this. And then it'll actually tell you whether or not you survived. So let's see. Jenny, what class do you want to be? First, second, or third class?
Which is first class good?
Yes, first class, most first class people survive.
Okay, then to confuse things, I'll put myself as in second class then.
Okay, good, I like that. Straddling the middle line. Age, you are 20. How many siblings do you have? Siblings or spouses, that's 2. Parch, I don't remember what this stands for. I'm gonna leave it. I'm gonna say you paid 10 pounds for your fare. Why not? And you are a female. Okay, good. Now, if we run this should tell us whether or not Jenny would have survived. She did survive. A 1 mean that she lived. So yeah.
Yay.
Lots of excitement.
Only 82% accurate though.
That is true. That is true. You would never know. I guess we would never really know if Jenny survived, but it seems like, what if she was 87? Great question. Let's try again. What would happen if Jenny was 87? Actually, we can just run this. Oh, she died. Dramatic. That was it. That was the determining factor, her age, unfortunately. All right, yeah, so you guys can put in more passengers. You can put in yourself and see if you would have survived, which is both interesting and mildly scary, I would think. But, you're not on the Titanic, so good news, I guess, for us. But that's all I have for you guys in terms of this demo. I know I went quickly, but we wanted to finish in the 1 hour.